Welcome back to Pike Mathematics. Today I want to talk about matrices and how they operate in Iota, as well as show you some functions that we've created that work with matrices. So let's go into the system. First, I want to look at the Help tab real quick. Go to Basic Help. And you scroll down. There's a hyperlink labeled matrices. Click on that. This table right here, matrix operations. These are all the functions that we've created that work with matrices. This first column, this is what they're called. And the second column, these are the keystrokes you need to use in order to call those functions. So now let's go ahead and demonstrate these. Go into a new paper. First thing we need to do is make some matrices. And in order to do that in Iota, you have to use square brackets. And you have to use one set of square brackets to go around the entire matrix. And then each row needs to have its own square brackets. So let's create M. It'll be equal to A, comma B. That's the first row. And C, comma D is the second row. All right, it's our first matrix. Let's make another one. We'll call it N, and we're going to put some imaginary numbers in here. We're going to go E, comma IF, and IG, comma H. All right, now we have two matrices. What can we do with them? The first thing we can do, probably the easiest thing, would be to add them up. So M plus N equals, there you go. And because their dimensions are compatible, M times N, we can take their product, and you get that. So let's talk a little bit about those functions I talked about. The first is the transpose. So if I want to take the transpose of M, type M, backslash TRA for transpose. There you go. That's the transpose. Basically, what the transpose does is it turns rows into columns. So the first row of M was AB. So now the first column of the transpose of M was AB. The next function we have is called the conjugate. So the N backslash CON. Okay. What the conjugate does is it doesn't move anything around, but all it does is it changes the sign on the imaginary numbers. The next function is called the hermitian conjugate. So if I want to take the hermitian conjugate of N, I go backslash DAG. Okay. So basically, the hermitian conjugate is you take the conjugate of your matrix and then you transpose it. And you can see that here. The first row here is E negative IF, and the first column here is E negative IF. Next thing I want to talk about is the, make a little room here. We'll talk about the trace. To use the trace, you go with capital T, lowercase r, parentheses, and put the matrix in the parentheses. And there you go. AD is the trace of M. Basically, that is the sum of the elements along this diagonal. And that's the diagonal that goes from the top left to the bottom right. What's kind of cool about the trace is that if your matrix has eigenvalues, then the trace is equal to the sum of those eigenvalues. Next thing I want to talk about is the determinant. To use determinant, it's DET, parentheses, put the matrix in the parentheses. There you go. There's your determinant. There's a lot of identities out there on determinants, and those are kind of fun to test in Iota. One is that basically the transpose doesn't impact the determinant. So here we took the determinant of M. What if we took the determinant of the transpose of M? And there you go. You can see that it's the same result. I also want to talk about the something called cofactors. Now, a couple of these functions are how you get the result. It's kind of convoluted. I don't want to get into all that detail right now. I just want to show you how to use these functions. And so cofactors is kind of one of those. All you write is cofactors, parentheses M. And there you go. There are your cofactors. There's another one called the adjoint. And that's just ADJ, parentheses M. And there's your adjoint. And what you see is that the adjoint is really just the transpose of the cofactors. So the first row here was D minus C. The first column here is D minus C. And the last but definitely not least, I want to talk about inverses. So if I want to get the inverse of M, all I do is raise it to the -1. And there's your inverse. if you want to kind of look under the hood of how the inverse is calculated, it's basically this: 1 over the determinant times the transpose of the cofactors. There you go. You can compare these and see that they're identical. So 1 over the determinant times the transpose of the cofactors. That's how you get the inverse. So these are the functions that we created. We think it makes working with matrices a lot easier. Truthfully, though, these examples I've given you, they're all 2 by 2. You can do most of those by hand without too much trouble. It's when you work with matrices, though, when the matrix gets larger, it gets much more complicated, and it gets much more complicated really quickly. So here's an example of that. Let me make a 4 by 4 matrix real quick. Let's see. There, you're going to have 4 by 4 matrix there. All right. What if I want the inverse of this matrix R? R, raise it to the -1. There we go. Even for the software, it takes it a little while. It's and you'll see why here shortly. There you go. That is the inverse of R, of a 4 by 4 matrix. That's a lot of work if you want to do that one by yourself. That's where we think Iota offers a lot of advantage, and we hope you try out these functions and agree with us. Now I want to show you another example, kind of a practical way to use matrices to solve problems. And I've already started that in another tab here. So let's say I've got a system of linear equations, and I want to figure out what the variables are that make those equations true. Well, I got this problem here, these 3 linear equations. I actually pulled this from Mary Boaz's Mathematical Methods in Physical Sciences book. It's the 3rd edition. This is chapter 3, section 6. It's problem 22 on page 123. That's where I pulled this example from. But I'm going to show you how we're going to solve it in using Iota. Basically, what you want to do is take this system of linear equations. You want to kind of convert it into a matrix format. The first thing you do is you create a matrix that is comprised of the coefficients of the equation. So I've done that here with H, and then I want to create a second, basically a column vector. I'm calling that capital X, that is comprised of the variables X, Y, and Z. And this is what we're really trying to figure out. What is X, Y, and Z? What are the values for X, Y, and Z that make these equations true? And you can see here when you multiply X or H times X, you get the same equations as you see right here. Now you have to make you also have to make what I called B, and it's another column vector, and it's equal to the result 4, -1, and 5. So that ultimately the kind of the full transformation into a matrix format is HX equals B. Well, to find X, what I can do is if I multiply both sides by the inverse of H, I'll get the answer. So let's try that. H to the -I times B equals. All right. So these are the values for X, Y, and Z that make these equations true. If you wanted to test that, you could put 1 in for X and -1 for Y and 2 for Z into these equations and see if it's true. But we think we have a pretty cool way and quick way to do that as well. I'm going to create another matrix. And this is kind of, I'm not sure what the right word is, if we call it a matrix function or matrix-like or function-like, but it looks like this. So I'm going to create a matrix, and I'm going to make it a function of X, Y, and Z. And then its rows are going to be these equations. So the first row is X minus Y plus Z. The second row is going to be 2X plus Y minus Z. And the third row is going to be 3X plus 2Y plus 2Z. All right. Now I'm going to plug in these values that we got back and make sure that this is the correct answer. So C of 1, -1, 2 equals, there you go, 4, negative 1, and 5. That's what we'd expect to get. So it worked. We think it's a useful and quick way to solve systems of linear equations. I have one more example I want to show you, and that's using matrices to do rotations. And I've already started this problem as well. This is this matrix right here is kind of a classic matrix for rotating a vector by theta degrees in a counterclockwise fashion. And again, I've used this kind of matrix function that we've created here, and it's a function of theta. And we're going to rotate this vector, which is essentially the x unit vector. All right, so let's say I want to rotate v underscore 1. How would I do that? Let's say I want to rotate it 90 degrees. I'll do it this way. First, I'm going to call this new function v underscore 2, and I'm going to say it's equal to m, and we're rotating it. Theta is going to be 90 degrees, so m of 90 times v underscore 1. There you go. So that's when you rotate v1 90 degrees, you basically get the y unit vector. Let's try another one. We'll rotate it 180 degrees. Oops, v underscore 3 equals m. There you go. So now it's pointing in the negative x direction. So we can go ahead and graph these. I'll insert a graphic. We're going to add a grid first so we can see where we're working. There we go. Now I've got my grid. Let's graph V1. So I select vectors, change this origin to 0. And I don't need to type in the vector. I can just use the vector reference that we created here. So we're just going to call it v underscore 1 like we did in the console. Then we got a legend, so we're going to properly label that, and we'll make this thing red. Let's see if it shows up. There you go. There's the x unit vector. I'm going to append it and add it to our graph. I can do the same thing with v2 that we already created, except we'll make it blue. There's the first rotated vector. What about this third v underscore 3? I could similarly just reference v underscore 3, but I want to show you that the system, this box here, can actually do math itself, and it understands this rotation matrix here. So what if I just put m of 180 times v underscore 1, and I will change the legend here, and we'll make this one yellow. Let's see what happens. There you go. It works. So the point here is that this box can do the math as well. Okay, now I'm going to make another matrix. I'm going to make it a function of phi. You know what? I want to do that a little bit. I want to do this a little bit differently. I want to copy this. I'm going to show you how to copy things. So we can do Control C. I need to move this graphic down though first. Do that. Make a little space. Okay. Now I can copy that matrix right there, but I'm going to change it to n. And it's going to be a function of phi. These will all be phi's. There we go. Okay, so I've got this new matrix, and it similarly rotates in counterclockwise fashion, but by phi. What would happen if I take m times n? Well, let's figure that out. So I'm going to make another function, and I'm going to make it a function of theta and phi. And I'm going to make it equal to m of theta times n of phi. There you go. So here's our new matrix. And this kind of demonstrates that Iota understands a number of trig identities. So it's simplified these entries to the trig functions that are the sum of theta and phi. So now I can let's do another rotation here. we will make a v underscore 4, and it's going to be equal to r of, we'll make theta 180 degrees, and we'll make phi 45 degrees. And again, we're going to rotate v underscore 1. There you go. So that's v4. We can go ahead and graph v4. Put it in here. We'll make like a blue. Okay, there it is. There you go. That's so theta rotated 180 degrees and phi, rotated another 45 degrees. You'll notice I kind of made a mistake here, and I didn't label this green arrow as V4. I can change that. If I look at the script, you can see these are the legend titles. I'm going to go ahead and change that to V4. And if I hit the red button, it's going to correct it. There you go. All right, last thing I want to show you is I'm going to insert a table. Insert a table. Looks like I'm going to label this vector. Vectors. I'm going to label that theta. Label that phi. And we'll call this rotated. Oops. Sorry. Rotated vectors. All right. I'm going to populate this first one with v underscore 1. There you go. And let's say we want a theta to be, we'll make theta 180 degrees again. There you go. We're going to make phi 90 degrees. Okay. And then the rotated vector is going to be equal to r of 180 and 90. Oops. Here's a smarter way to do it. We're going to make all the trouble making a table. We're going to reference the cells. So instead of writing in 180, I'm going to reference B2. And instead of writing 90, I'm going to reference C2. Oops. And then instead of writing V underscore 1, I'm going to reference the A2. Let's see what we get. There we go. So it rotated the X unit vector and basically turned it into the negative Y unit vector. Let's graph that one. What I want to show you is that if you click this little settings box right here, this is the settings for the table. If I click onto this into the cell, this is telling me that cell is T73D2. Okay. I'm going to go over here and I want to graph that. So I can just make a cell reference and graph that as well. So T73D2. I think we're up to vector 5 at this point. We'll make it pink. And I'm going to test this. Look at our graph. There it is. I'm going to append it. I'm going to close all these because it's getting a little congested. All right, so there's all our rotated vectors. And the point here, I wanted to show you there's a lot of different ways to graph these things. You can make these references to the vectors you've created. You can have the graphing system do the calculation itself, or you can do the work in a table and reference that cell, and you get this nice graph. So I think that's all I wanted to talk about today. I hope you found this useful, and we thank you for taking the time to listen and watch this video. We think Iota has a lot of capabilities in the world of matrices, and we hope you find these functions and capabilities useful. Please email us at support@pikemathematics.org if you have any questions or concerns or any suggestions. We look forward to hearing from you, and please look out for future videos.